Welcome to another video session on Unit 4. We are looking at the combinational logic circuits. This is the third video session. In the previous sessions, we had looked into the Boolean algebra and the theorems and postulates associated with the Boolean algebra. We also looked into the standard forms of representing the Boolean equations and also the canonical forms, and how we can convert it in terms of min terms and max terms. And we have also looked into the basic gates and the universal gates. In this session, we will look into what is called as map technique or the map method. What is this map technique or map method? Why is it used? How is it used? Is what we are going to look into in this video session. So map basically is a graphical representation of the truth table. All right, and it is a straightforward and a simple procedure that you can use to minimize any Boolean function. It is also called as corner map or the K map. It is made of squares, and we are going to represent each square with a min term of the function. And we are going to group those squares and reduce the number of variables and thereby minimize the Boolean function. For example, if we are having a two variable function, let us say f of x comma y, so x and y are the two inputs for the function. It can be a two input AND gate, two input OR gate, NAND gate, or anything. So x and y combinations will be 4. So therefore, we have 4 minterms, and each minterm is represented in a square. Now, how those squares are written down, there is some rule in writing down. So let us look at how we write it down. So this is how we write down the first minterm M0, M1, M2, and M3. Now, how did we arrive at this combination, or how did we arrange in this fashion? Is by taking we know the two variables are x and y. So x can take the value 0 or 1, and y can take the value 0 or 1. So for the combination 0, 0, we get the minterm M0. So this is the position for M0. For x 0 and y is 1, we get the M1 minterm. For x is equal to 1 and y is equal to 0, M2, x is equal to 1, y is equal to 1, M3. So this is how we are writing. So you can write x here and y here. So x is the most significant bit and y is the least significant bit in these two bits. So x has a higher binary value compared to the y. Okay, so this is the corner map. Now, if you take an example of an AND gate, now this is AND gate. AND gate is 1 only when x and y both are 1, and for all others it is 0. So we indicate only the true value with a 1, and when the output is 0, we leave it blank. So therefore, the output of this from this map is that there is only a 1. So output is xy. Both x and y are high to get this. So if you consider the OR gate, so we have 3 1s. That is when x is 0, y is 1, and when x is 1, y is 0, we get a 1, and when x and y both are 1, we get a 1. So we get 3 1s. All right. Now we are going to do the grouping. So we have represented each minterm in a square, and for M0, the minterm 0, output is 0, so we are not entering anything here. It is left blank. Now we can do the grouping of these ones. for which the function values are high. So how do we do the grouping? The grouping can be done in terms of base, two powers. That means 2 power 2 power 1, that is 2 terms, 2 power 2, that is 4 terms, 2 power 3, 8 terms, and so on. So that means I can, at any time, I can group two number of ones, or 4 number of ones, or 8 number of ones, and so on. So in this, I have 2 number of ones which are adjacent to each other. I cannot club the numbers that are diagonal to each other. It should be adjacent. That means for this square, it should be above it, below it, or to the right or to the left. So for this, I can club it with these two, or for this, I can club it with this. So therefore, I have two groups. So I get two groups. But if you actually write the output for this in terms of the minterms, M1 will be x complement y, and M2 will be x y complement, and M3 will be x y. So if you write the function form in terms of the minterms, it will be M1 or M2 or M3, which will be x complement y or x y complement or xy, right? Now, when we have grouped this, one variable which changes state will be eliminated. Now, when we group these two, y remains same, that is y is 1, so y remains, whereas x takes the value 0 and 1, so x is eliminated when we do a grouping of these two. Next, when we have taken a grouping of these two, x remains the same and y changes state from 0 to 1, so y is eliminated by grouping this. So the group, when we group this, we get x. When we group these two, we get y. So we get two literals, x and y. So by doing these two groups of grouping, we have covered all the ones. There are no more ones left, and all the ones are covered. So we, as I said, we cannot do the grouping diagonally. So it has to be adjacent, not diagonal to each other. And only one with a 1 only will be grouped. And the grouping should be in powers of 2. 2 power 1, 2 power 2, and so on. All right, so that is 2, 4, 8, 16, 32, and so on. So we have done the grouping. Now we see, if you want to implement this equation by the Boolean equation as it is, so we require 1, 2 NOT gates to get x complement and y complement. We need one AND gate here to get the output of this. We need another AND gate here. We need another AND gate here to get xy, xy complement, and x complement y. And we need one OR gate with a 3 inputs. So 1 input, 2 input, and 3 input. So this many gates we require to implement this function. By using the map method, we have reduced this equation, and it just, the same function can be now, after reduction using the map method, we are using only one 2 input OR gate to realize this. Therefore, the cost is reduced and the delay is reduced. All right. If more circuits, more delay will be there. If less circuits, less delay will be there, because the output has to propagate from one gate to the other when we have cascaded them. So therefore, the delay also is reduced. So this is an advantage why we use the mapping technique and why we have to reduce the variables. All right. So I hope the two variable map is clear. So this, we have to remember that we have to arrange this in this fashion. How we do that is by taking the values of x and y, which can be the combination 0 and 1. So by taking arrange in this fashion, we are able to find out where the minterms positions will be. Okay, right. So let us take for a 3 variable. So this is the way we have arranged for a 3 variable. So two rows and four columns. Now why is it like this? Because we have taken two variables this side and one variable. So this x is the most significant bit and z is the least significant bit. So x, y, z. So x is 0, y and z both are zeros. So this is m naught, this is m1, m2 and m3, m4, m5, m6 and m7. So you can see the combinations of zeros and ones of x, y and z, and then identify where the minterms are. M0, M1, M2, M3, M4, M5, M6 and M7. So that is why we have written like this. Suppose you take x here and yz this side, then you will have two columns and four rows. So it will be different. Okay, so you can try that as an exercise and identify where your M1, M2, M3, M4, M5, M6 lies by taking the combinations. All right, so you can try that as an exercise. Okay, now let us come back to this. So depending upon how we choose the variables here, we get the positions of these M0, M1, M2, M3 minterms up to M7. Okay, now let us realize a function. Simplify the Boolean function. So this is a function represented in terms of its minterms. So as you know from the representation, sigma means it is a sum of products. So product is nothing but these minterms. So they are expressed as a sum. So output is high for M2, M3, M4 and M5. So therefore, if you take the same map, the same corner map and put 1 for the corresponding minterms. So that is M2, M3, M4 and M5 are the ones. The blank ones are zeros. Okay, and we have to start grouping now. Okay, so if we start grouping, without grouping, you see what will be the expression. F will be equal to x complement yz, x complement y z complement. This will be x y complement z complement. This term will be x y complement z. So there will be four terms, four minterms, right? Now by grouping this, these two can be grouped and these two can be grouped. As I said, these two cannot be grouped because they are diagonal. So these two will not be grouped. So as I said, you can start grouping in terms of 2, 4, 8. And how those grouping has to be done, they have to be adjacent. Though there are 4 ones, you can't group all these 4 because they are not adjacent. These two are like a diagonal. So we can't, suppose if these two ones were here, then we could have grouped all these 4 because they are adjacent squares. So since it is not in that fashion, we are going to group these two together and these two ones together. So whenever we club, we see that the variable which changes the state will be eliminated. The variable which does not change the state will be retained. Now here in this row, x takes the value 0, so it is x bar, whereas y takes the value 1 and z takes the value 1 and 0. So z changes state and y does not change. So whichever changes state will be eliminated. So we get this as x complement y. Similarly, for these two grouping, y remains same and that is y complement, and z changes from 0 to 1. So therefore z changes again, and here x remains same. So it is x y complement. So this grouping results in x y complement. This grouping results in x complement y. So we have done the grouping, and if you we have simplified that from 4 terms, we have now reduced to 2 terms of 2 literals each, which is x complement y or with x y complement. So we have reduced the Boolean function. And if you see that, we can realize it with less number of gates, unlike the previous without, where the function is without simplification or without reduction using map. All right, so this is one example. Let us take another example for a similar three variable function f of x, y, z, and the function is high for M3, M4, M6, and M7. These are the minterms. So it is expressed in sum of product forms, SOP forms. So if you draw the Karnaugh map for this, so it is M3, M3 is here. So we have arranged in the same fashion, M0, M1, M2, M3, M4, M5, M6, and M7. So we have to identify the outputs for which for the minterms for which the output is high. That is M3 is 1, M4, M6 and M7. Now again, there are 4 ones present but not adjacent. So these two are adjacent, these two are adjacent. Okay, so therefore these two can be grouped, these two can be grouped. Next, if you see, by grouping these two, what is remaining constant or what does not change state? X changes state, whereas y and z does not change state. So y and z both remains 1 1. So this, by this combination, by this grouping, we get yz. By this too, we get, or rather we need not keep, so we our whole point should be to group all the ones. So this one is already grouped here, so therefore we are not going to group this again, because this one can be grouped with this. Now you can ask me, they are not adjacent, how are you going to group this with this? Now this, the speciality of this Karnaugh map is that when you fold it or rotate it, this edge will go and sit at this edge, right? So that is the advantage or the um, feature of this Karnaugh map. So when you fold this, these two cells becomes, or these two squares become adjacent. So therefore they both can be clubbed. So because this edge will go and sit at this edge, so this cell will come here. So they both are adjacent. So therefore M6 and M4 can be grouped. Suppose if you want to fold it along the y-axis, so therefore M4, so M0 will come and sit at M4. And similarly, already this is, they both are in the same adjacency. Okay, so therefore, but only the adjacency we are considering is for these two. Okay, similarly, when we fold this, M2 will be adjacent to M0. As we have said, M6 is adjacent to M4, M2 will be adjacent to M0. Now they are not ones, so we are not bothered about that. So these two are, what is the minterm for M4? X, Y complement, Z complement. What is the minterm for M6? X, Y, Z complement. So when we club these two, as I said, which is changing the state, X remains as 1. And in this, what is changing the state when you take these two combinations? Y is changing from 0 to 1, whereas Z is staying the same state, 0 and 0. So therefore, Y will be eliminated, X and Z complement will be there. So therefore, X, Z complement. By the combination or grouping of these two, we got X, Z complement. So the four function, the four rather the four terms with the three minterms but three literals is now reduced to two terms with two literals each, right? So yz or xz dash. So we have reduced with a function which was with four terms is now reduced to two terms of two literals each. All right. So therefore, we have reduced the Boolean function. Now let us simplify with another example. Now in this case, the output is high for M0, M2, M4, M5, and M6. So if you draw this, now this is just to explain how they are adjacent. Okay, so we can club the four. Now 1, 2, 3, 4. So these four are, I said, they are adjacent. As I said, we can, when we fold this, M2 will be adjacent to M0, M6 will be adjacent to M4. So you can have a 4 combination. So when you fold this, this 2 will come and sit next to here. So therefore, all the 4 are adjacent. So when you club four variables, I mean four minterms, then for one, I mean for one combination of two, that means you are joining one and one literal will be eliminated. Now when you're joining four numbers, four squares, then two literals will be eliminated. When you are joining eight, three will be eliminated, and so on. All right. So the whole point is we have to identify, or we have to group all the number of ones wherever they are present. So when we write it in this fashion, it is easier to group the ones. Otherwise, we will blindly write somewhere and we will not be able to group properly. That is why we follow this pattern, so that we identify where the minterms are and grouping becomes easier. All right. So that is why we write it in this fashion. Okay. So while grouping these four together, the result of these two will be the result of these four combinations will be Z complement. All right. Similarly, there is one left here. So this has to be clubbed with something. So it cannot be clubbed with this. It cannot be grouped with this, nor with this, nor with this, but it can be grouped with this because this is the only adjacent square for this M5. So therefore, when you club these two, so what is changing the state? Y remains as Y complement and Z is changing from 0 to 1. So Z will be eliminated. So when you club this, it is X Y complement. So therefore you have one term and another term for these four combination, which is Z complement. So therefore the function is now reduced to F is equal to Z complement or XY complement. So this is the function. So whatever the output you get by using this equation will be same as whatever output you will get by using this equation. But what is the advantage? The advantage is you are using less number of gates to implement this function rather than this function. So that is the advantage. Now let us take another example. So for this Boolean function, f is equal to, again, it's a three variable function, a, b, I mean a, c, a, b, c, all right, with different combinations of the minterms. All right, so we have to express this as a sum of minterms, and we have to find the minimum sum of products for this expression. So this is an alternate way of asking the question. So they have given in terms of the ABC minterms, and they are asking you to express this as a sum of minterms. That means sum of minterms will have all the literals, right? A, B, C literals, whether it's complement or whatever. So we have to fit in all the three. So each term will have three literals. So this is correct. This is A is missing. That is A's literal A's position is missing. In this literal C's position is missing. In this literal B's position is missing. So we have to fill in all that, and then we can express as a sum of minterms, and then we have to simplify this by using the corner map. Okay, so first we identify the function for this as okay. So this is the function, and it is 1, 2, 3, 5, and 7. So M1, M2, M3, M5, and M7. All right. So we have done the entries, put ones for each of these minterms, and we have done a 4 grouping and a 2 grouping. And for 4 grouping, 2 literals will be eliminated, and your resultant literal will be C. And in these 2 grouping, I mean in the 2 square grouping, you have 1 literal eliminated, and the result is A complement B. So we have reduced this to a function C or A complement B. So this is the sum of the minimum. All right. So we have simply written here the simplified expression. All right, with minimum sum of products. So this is the sum of products. This is the products. These are the products and the sum. So sum of products. So it is the B solution. and this is the sum of all the minterms. That means by rearranging or adding all the missing minterms, you will get this function value. And then this is already done by using the previous case. That means a similar problem we have solved in the previous exercise. You can check that. So we have got this result from there. Okay. So next, let us look into a 4-variable K map. So when we have 4 variables, how does the K map look like? This is how it looks like. So you have M0, M1, M2, M3, M4, M5, M6, M7, 8, 9, 10, 11, 12, 13, 14, 15. So you have the total 16 squares. So how do we write that? This is W, X, Y, Z. So they are the 4 variables. W is the most significant and Z is the least significant. So they will have 0, 0, 0, 1, 1, 1 and 1, 0 combination. So as I said, we have to follow this pattern, M0, M1, M2 and M3. So therefore, this will be 1, 0 and 1, 1 combination. So similarly, this will be 0, 0, 0, 1, 1, 0 and 1, 1 combination. So for this is the way you write down, because it will be easier to identify the or group them. If you write it in any other fashion, you will not be able to simplify further. So if you write in this fashion, you'll be able to easily group them into terms of 4s and 2 and 8 and so on. So now these 4 are, you can club anywhere 4s. So this can be a 4, this can be a 4 combination, this can be a 4, this can be a 4, this. So for row wise 4 combination or a column wise 4 combination, or 2 rows and 2 columns can be 4 combination. All right. So if you want to go for an 8 combination, it can be 2 rows and 2 columns. I mean 4 rows and 2 columns, or 4 columns and 2 rows. We will get 8 combinations. So 8 number of squares can be grouped like that. So for 16, all should be 1 so that you can get a 16. So there are different ways of grouping this. And again, as I said, like the previous cases, when we fold this, M2 will be adjacent to M0, M6 will be adjacent to M4, M14 will be adjacent to M12, M10 will be adjacent to M8. Similarly, that is folding along the y-axis. When you fold along the, it's folding along the x-axis or folding in the vertical direction. If you fold this in the from top to bottom, this is from folding from left to right or right to left. When you fold from top to bottom, M0 will be adjacent to M8, M1 will be adjacent to M9, M3 will be adjacent to M11, M2 will be adjacent to M10. So that will be the adjacency for this 4-variable map. Okay. So I hope the which will be adjacent, it will be clear. It is clear from this 4-variable map. Okay, let us take a simple example and do the grouping simplifying. Okay, so f is a 4-variable function x, w, x, y, z, which whose minterms are m0, m1, m2, m4, m5, m6, m8, 9, 12, 13, and 14. So we are identifying. So this is m0, m1, m2, m3 is not present, m4, m5, 6, 8, 9, 12, 13, and 14. So we have to start grouping. So we can group this into 8. So these are the 8 grouping. So when we do the, as I said, if you group 2 squares, 1 will be eliminated. 4 squares, 2 literals will be eliminated. When we have 8, then 3 literals will be eliminated. So by doing this combination, you see what all are changing. So W and X are changing, and then Y is remaining as 0 and Z is changing from 0 to 1. So 0, all these 3 literals are changing states, only Y remains same as Y bar. So or Y complement. So the combination of these 8 ones will give us Y complement. And next, so these four, these three ones are left out. So we can do again 2 and 2 combination. Since we want to reduce it more, so we can club these 2 with these 2 ones. As I said, when we fold this, these 2 will come in adjacency with these 2. So M6, M4 will be adjacent, M14, M12 will be adjacent. So we'll have 4 combinations. So when we have these 4, so we can reduce it as this. So what is this term? So this will be X, W, so these 2 will be X, Y complement, Z complement, because W is changing state. So here again W is changing state. So these 2 will be X, Y, Z complement. Next, when you club these 2, so you have got the result here: X, Y complement, Z complement, and Y, X, Y, Z complement. So when you club all the 4, which is changing state here, Y complement and Y, so that will be eliminated. So if you take out X, Z complement as a common in both of this, so you will be resulting with X, Z complement multiplied by Y complement or Y. So what is Y or Y complement is equal to 1. So you have ended up with X, Z complement. So therefore, we have resulted with this. The combination of these 4 have yielded X, Z complement. And similarly, these 4 can be clubbed and we end up with Z complement, W complement, Z complement. So therefore, we have got the result as Y, Y complement for the combination of these 8, and W complement, Z complement for a combination of these 4 together, and this one is still not clubbed with anything. So for that, we have clubbed these 2 and these 2 together. So we have got X, Z complement. So therefore, the function of so many literals is now reduced to a function of only 3 terms of 1, 2, 2 literals. All right. So such a long expression can be simplified and realized using very few number of gates. So that is the advantage. Let us take another example in another way form, that is given f is equal to ABC. That means it's a it's a 4 literal. It's a 4 variable function ABCD, and we have to find out by filling in all the remaining missing terms, and we get this output 1 1 1 1. So these are the outputs. So by clubbing all this in a similar way, we have reduced the function f from 4 terms to 3 terms, and and here it is 4 literals, 3 literals, 3, 4 literals, 3 literals. We have reduced to 2 literals, 2 literals, and 3 literals. So we have simplified this equation from here. Okay, so this is how we have solved this problem. Okay, so when we are grouping, there are something called as prime implicants. So when we choose these adjacent squares, now they become the prime implicant. So let me take an example here. So they are, okay. So when we have clubbed here, okay, so let me go through what are prime implicants, then we can go. So when we choose the adjacent squares in the map, all the min terms should be covered. So those are called as prime implicants. So it will cover the major of them. So those are called as the prime implicant. So a prime, in other words, a prime implicant is a product term obtained by combining maximum possible number of adjacent squares in the map. And uh, if the min term in a square is covered by only one prime implicant, that prime implicant is called as the essential prime implicant. So now let us take an example and understand this essential prime implicant. So you have a function, AB, it's a 4-variable function, and the outputs are 0, 2, 3, 5, 7, 8, 9, 10, 11, 13, and 15. So we identify the points, I mean the min terms, and so we have grouped these four. And as I said, when we club, these two will come adjacent. When we fold along the top to bottom, these two and these two will come adjacent. So they four can be grouped as a four. So we have taken these eight, these four as one group and these four as one group. So therefore, we have ended up with two terms, B, D and B dash, D dash. All right, or BD and B complement, D complement. So by combining these two groups, this is one group which results in BD, and these four, when we combine together, we have we obtain the result B complement, D complement. All right. Now we have that means we have taken only few of these. That means we have taken M naught into consideration, M2 is taken, and M3 is not taken, and M5 is taken, M7 is taken, M13, M15 is taken, M8 is taken, M10 is taken. So left are M3 and M9. All right, so these two we have not taken into consideration. Now once, I mean M11, M3 and M9 are not taken into consideration. Okay, now with that we have obtained the, so that means we have done a maximum of 4 and 4 combination. So we have got the implicants. So these are called as prime implicants. All right, so these terms whatever we got, so they are called as the prime implicants. Next, the remaining literals we add in, and we try to again simplify. So that is M9, M11 and M3. So when we add these four again and start grouping them into fours, so these four, and these four. All right, since all other things are already taken care in this previous two, so they are prime, so that means they are already clubbed once, already grouped once. All right, and now for the remaining number output ones, or the remaining min terms, we are trying to group and find out the, so we end up with 4 different prime implicants. So from this we have to identify which are the ones. So we will get different results by using these different prime implicants. So these are the essential prime implicants. So prime implicants means after you club whatever the result you get, so they are called as a prime implicants. Okay, so we have the 4 prime implicants here, that is CD, B dash C, AD and A B dash. Now from this we can get 4 different, these are the essential prime implicants, and these two, so these 4 can be taken in different ways. So 4 different equations we get. So these two are the essential prime implicants, and these are the other combinations. So therefore we have 4 different expression for F by using this essential prime implicants and just the prime implicants. All right, so in this session we had looked into the map method. In the next session we will look into the product of sum, how we simplify the POS form. We'll continue in the next session. Thank you.